Hello everyone. Let's discuss about B plus trees now. So what is a B plus tree? As we know, as the name itself indicates that it's a tree, and as such the data is stored in the form of a tree, so that you'll be finding a hierarchical structure. That is fine. Now when you consider with respect to databases, B plus tree is said to be a balanced binary search tree. As you know, simply a binary search tree which is used to search an element in a tree, so that we can be able to retrieve that particular element from the entire hierarchical structure. This B plus tree is said to be a balanced binary search tree, and this follows multi-level indexing structure. Okay, so what you'll have here is any tree, when you consider a tree, you'll have a leaf node, and this leaf node will determine the data pointers, nothing but the address values. And B plus tree, as we say, it is a balanced binary search tree. It will ensure that all the leaf nodes are at the same height, and these leaf nodes, as they contain index values, each of the leaf node is connected via using a linked list. This is how you can see here. You can see the leaf node, and the end of the leaf node is connected via a pointer with the other node. Okay, and this is said to be the data node, the root node. From here you will be identifying which has to be placed on the left of D and which has to be placed on the right of D. Okay, from there, and each of it, this entire set is said to be the left of D. That is fine, and this entire set is said to be the right of D. Even that is fine. But when you need to access the data from this particular database, both these different sets must be actually joined by using a linked list. So if you can identify this, these are in the form of a list of data items, and all these list of different sets of different lists of data items are connected via a link to each other. Actually this list belongs to left of D, and this big list belongs to right of D. This is what it determines, and all the leaf nodes will be at the same height. All the leaf nodes will be at the same height. And when you say it's a tree, the B plus tree, it follows multi-level index structure. Multi-level index structure, and these leaf nodes actually determine the data pointers. Okay, so that is what is a B plus tree. Now let us see how to search for a record in a B plus tree, as well how to insert a record and delete a record. See, all the leaf pages, if you can understand, this is the actual structure of a B plus tree. These are said to be the non-leaf pages, and this particular part is said to be the leaf pages. And all these leaf pages are sorted by search key. So all these leaf pages, they will be containing all the data entries, and each of this set, called as a list, are linked by using some chain something here from previous to the next. And this is all about leaf pages. If you consider the non-leaf pages, these non-leaf pages will have index entries, like you'll have the left entry, left address pointer, and right address pointer. Okay, now this left address pointer is used to hold certain leaf nodes, and right address pointer is used to hold certain leaf nodes. These two different leaf nodes are said to be different sets or different lists. Now these two lists are linked by using some chain here. Okay, so these are all said to be leaf pages, and these are all said to be non-leaf pages. These non-leaf pages will be having these index entries. By using those index entries only, we will be able to search for an element or insert for an element in this particular leaf pages sector. So how the index entry, it is something like this, like a key and a value in terms of, you'll be having, see, this is a value, k1 is said to be value, and p0, p1 are its two pointers, pointer not pointer 1. That is the left, this is called as the left side of k1, and this is called as the right side of k1. Okay, so this left side of K1 will be pointing to some values, and this right side of K1, right pointer of K1 will be pointing to some other values. Clear? Next, the same right pointer of K1 is now the left pointer of K2, and this will be handling some values, and there is one more thing called as the right pointer of K2, and this will be having some more data elements, nothing but leaf nodes. All those are nothing but leaf nodes. So each of these pointers will be handling some type of data, some data, depending upon the condition that we'll see in the example. Now suppose you wanted to search for a record in this particular witness tree. This is the actual tree which is stored. This part, this is said to be the non-leaf node, and these are all said to be the leaf nodes. Leaf nodes are the nodes which actually contain the data, the actual data. These are all non-leaf nodes, nothing but they are used to contain index pointers, and by using these index pointers you will be able to retrieve the data. So suppose this is all the data located within the leaf nodes, and suppose you wanted to search for a record. Suppose you wanted to search for a record in witness tree. Let us suppose that record value or data value is 55. So it is pretty clear that this value 55 is available in the leaf node. That is what we are going to search always. So when you wanted to search for this thing, so you should first of all identify what is the intermediary node for this 55. For that you should search for the non-leaf pages. So the non-leaf pages or non-leaf nodes here are 25, 50 and 75. And now if you wanted to search for a value which is nothing but 55, 55 is actually or lies actually in between 50 and 75. So the intermediary node is available in between 50 and 75 for a value called as 55. So we will understand that this 55 will be available in the pointer, right pointer, because this 55 value is greater than 50 and less than 75. So it will be available on the right pointer of 50 and left pointer of 75, and hence to where it actually points to, that is nothing but there you will be finding a 55 here. Here DBMS will perform a sequential search in order to identify 55. One thing which I should make you clear is uh, this B plus tree uses both the sequential search as well as the random search. So when you are identifying a node called 55, you are in a procedure to identify the intermediary node. Yes, that is obtained between 50 and 75. That is nothing but called as random search. And here, after coming here, you will be moving towards this. That is said to be a sequential search. Even this, we can say it as a sequential search, because in order to come to 50, first of all, you need to trace from the beginning. So it is a sequential search. So now DBMS for this particular example has performed a sequential search in order to identify a data node, a leaf node, or data value called as 55. Okay, suppose our next our next task is to insert some value into the B plus tree. Okay, so let us take an example called 60. You are trying to insert a value called 60. So where this value can be inserted? This value can be inserted in between 50 and 75 because it is greater than 50 and less than 75. Fine, when you are trying to insert here, already there are 4 entries for this particular intermediary node. All those 4 entries are finished, completed. So there is no space for 60 now. So what to do? We don't have space to insert 60 here. In such a case, what you should do is you should go for the option of splitting the leaf node. Splitting the leaf node, because which leaf node? You have many leaf nodes here. You have many leaf nodes here. Which leaf node? The leaf node where this 60 can be inserted. That is this particular leaf node 50, 55, 65 and 70. This must be splitted up. So when you split up this, only then you will be able to store 60 into this particular leaf node. So when you split up this leaf node, it will be divided into two parts. Okay, it will be divided into two parts in such a way that I'll group up. So you'll have all the values called 50, 55, 60, 65, and 70 will be the values now. Okay, so what we finally decided, we decided to group them. When we try to divide them, it will be divided into two parts, and in these two parts the data must be entered. So when you try to enter the data, you will be grouping 50 and 55 and the other group as 60, 65 and 70. So this looks like this. 25, 50. Remember here you have in the leaf node, in the non-leaf node, you have 25, 50 and 75. You wanted to insert 60. There is no space, so you are dividing. So you'll be divided into two parts. So it will be 50, 55 as one group and 60, 75, 70, 60, 60, 65, 70 as another group. That is fine. Now where this 60, 65, 70 has to be stored, that is what we should see. So when you grouped up, when you divided this, you can't point it from both the you can't point the same 50 for both 50, 55 and 60, 65 and 70. As a result, in order to prevent such dilemma situation, what do is you just, when you group up as it is getting divided into two parts, you try to add one more node, root node, into this non-leaf nodes, because you cannot have an entry something like this from the same entry point. From the right pointer of 50, you can't have for both 50, 55 and 67, 65, 70 group. As a result, you'll add one more node called as 60. You'll add one more node called as 60. Where should the 60 actually placed, root node, when you consider? That should be placed in between 50 and 75. As such, we'll move the 75 to the other end and place 60 here, so that the left pointer of 60 and right pointer of 50 will hold values called 50, 55, and the right pointer of 60 will hold values called 60, 65 and 70. Is that clear? As a result, what you are having, you are getting two vacant spaces here in the leaf node, as well as one more vacant space here in the leaf node. Okay, see, this is how we can insert an entry. Suppose if you can remember your exam tree, if the same situation occurs, as you don't have space here, you'll just create a page. That particular page is called as an overflow page, and here you'll just try to add a value called as 60, and you'll consider this particular page as an overflow page. But when you come to the B plus tree, you don't have an option of creating an overflow page, because overflow page itself is a disadvantage, because we are going to create more space for the sake of just a single node or single data. Yes, so itself is an disadvantage. So you don't have overflow page in B plus trees. As a result, what you do is you just create one more entry here, that is 60, and for this you'll be creating 60, 65 and 70. This is how we'll be inserting a value called 60 into the table. This is how you'll be inserting a value called 60 into this. Now you have two more spaces here and one more spaces here. No issues. If at all, if you get one more value called 59, you can just insert here. 57, you can just insert here. If you have one more value called 74, you can just insert here. This is how we can insert an entry when there is an overflow. But we can't say this is an overflow page, because we are creating a node here, a root node here, and we are creating a link from that root node to store the data here. Okay, this is what happens with B plus tree insertion. Now, suppose if you wanted to delete the same 60, which you entered, if I just delete this 60, there will be no use of this 60, yes or no? So that also can be done, so that you can reduce the table. So you'll just remove 60 from the you'll have to remove data 60 from here. Yes, you'll be removing it. When you remove this 60, you need not, without the availability of this, you can store 65 and 70. As a result, you'll just store it here as 65 and 70. You need not have 60 again in the B list. That is as simple as such. So you'll just remove 60 from there, place 65, 70 back to its own place. Even from the root node, you will be removing 60. Okay. This is how we can create a balanced B plus tree. So this is how we'll have to create. We can search for a node in the B plus tree. You can remove a node. You can insert a node from the B plus tree. So this is the page. See, if you can remember your exam tree, you'll have one more page here called as overflow page. Whereas for a B plus tree, you don't have such overflow page. So the leaf node contains n record pointer and n key values are available, and every leaf node of the B plus tree contains one block pointer P to next point to next leaf node. So whenever you create, or the main goal of B plus tree is to have, we can easily search, quickly search, and there are no overflow pages. Just because of having no overflow pages, too much of what do we call, the space is getting saved, and we are having all sorted intermediate and leaf nodes. Since it is a balanced tree, all nodes must be in sorted fashion. Yes, it will be in a sorted fashion, and this is the basic structure of a B plus tree. You should understand, uh, which will contain the entry points, index entry points or pointers, and each set is linked via something. Okay, this is what is called as a B plus tree. This is said to be a balanced binary search tree, and it supports multi-level index structure. It supports a linked list. From the structure, you can say it supports multi-level index structure. It will be using linked list data structure. It is said to be a balanced tree. Okay, this is what we can infer from the structure itself. So it is very easy, and if you wanted to have insertion, if there is a scenario something like this, what you do is you'll just split up and just add here, rather than creating overflow pages. You'll add a new node. See, the thing is, you will not have any confusion here where the problem is. So you can just add a node here, a root node, and you can just have pointer values to point out to the other nodes. This is how we can insert the value. When there is no space, this is the procedure. If there is a space, you can just add up simply. And if you wanted to delete, if you are trying to remove it, and if you could accommodate the other two into its own previous place, you can do it just even by removing it from the intermediary node also. Okay, so all, when you come to the advantages, all the nodes will be in sorted order. You can do it because it is in sorted order. You can do sequential search as well as random search also. There, because there are no overflow pages, you have good space utilization, as well as the usage of intermediary nodes containing pointers to the records also will create good space utilization. Is this clear? This is what is regarding B plus trees. Hope everything is clear. And if you have any doubts, you can please post it in the comment section. Thank you.